Well, welcome back, everybody. And we still have a very interesting presentation before us. And this presentation will be given by Professor Malin Åkermo from the Royal Institute of Technology in Stockholm. The title is Composite Manufacturing and Future Lightweight Design. So Malin is a professor in lightweight structures at KTH, and a special interest are composite materials and their processing. She's leading a group for doing research on manufacturing of structural composites, and she works very closely with composite industry. And she's working across a number of application areas from aerospace to automotive. So if you're ready to take over, Malin, it's all yours now.
Okay, thank you. Hello, everyone, and thank you for this opportunity, Kevin. It feels like we are David against Goliath, because we are now a very small department presenting compared to what we heard in the beginning of this conference, where Professor Warren told about his great network for composite manufacturing. I come from KTH Royal Institute of Technology, so we are still in the Nordic countries. We are in Sweden, in Stockholm. We are a fairly small research group, approximately 6 seniors. We have 2 affiliated faculty from industry working closely with us, and we have roughly 15 PhD students and some postdocs. Some of the PhD students are also employed by industry, so we make no difference if they are industrial employed or working at the campus full-time. We have all the same requirements for becoming a PhD. As Olle said, we work often in collaboration with industry and towards different applications. I wrote this title for the presentation quite early, and now I have to live up to it. So I was thinking what to say. And we have heard quite a lot already, and I'm afraid some of that will be repeated with other words from me. Talking about composite manufacturing, future lightweight design, I think we all understand and know that it needs to be cost effective. I think it has to include several different materials, still ensure sustainability. And in the future, it also have to deal with multifunctional materials and structures. So with that said, these are the 3 topics that I will actually also talk about, trying to explain how I see these things today and in the future, what we do today and what we will do based on what we have learned. So we will talk about cost effectiveness to start with. And I mean, we are a university. We do not know a lot about what it costs to have an industrial application, of course. But in order to understand what is important to work with, we have had a research program around predictive technical cost modeling, where we try to see what kind of different manufacturing processes there are and what can be produced with them, how fast are they, how many components can we make an hour, depending on how complex the geometries are, and make like a cost model based on that. The costs that we have, of course, are not industrial based. They are based on numbers that we can find in literature. So it is based on what it costs to build the new factories, sort of. But in this case, this way, we can compare different kinds of processes and materials requiring different process steps, which makes us understand a little bit more about what it's all about. So to me, cost effectiveness is to find the right level of automation for the material, geometry, and production volume required. And I think that's what we have heard with different words during these presentations. When you have that level of automation that is the best for you, you need to learn the process window for that process so you can really use it to its full potential. And then also, of course, ensure robust manufacturing and small geometrical tolerances to enable low-cost assembly. So now I will come deeper into these points, telling what we did and how we started and where we are going right now. And although we said that we work towards different industrial disciplines, I think lately, since I started at KTH, we have worked mostly towards aerospace components. And therefore, I will start with a typical aerospace geometry, and we will look at how we have worked on the kind of automation and around that. To us, a typical aerospace geometry is quite large. It has a flat outer surface and a lot of stiffeners, which include ramp areas, recess areas, and convex areas. So the flat area itself is fairly simple, while the different geometries can be quite complex. And you see there what we call the test geometry. We also call it the pair beam because of the PhD student who started working with it. And that geometry will follow through this presentation. The level of automation which we have been looking into for this particular case with the surface and the stiffeners is that we make a lot of layers, multi-layer layup using an ATL or an AFP flatly, or the outer surface can be made directly, of course, but we focus here on the spars. They can be laid up flatly and then afterwards formed in something called Hotep Forming, which is a process where you put your material as a stack. I think you can see my pointer here. On the tool, you have a rubber, you heat up the whole thing, and when you have the right forming temperature, you take out the air, and the pressure from the rubber will form the geometry towards the stack. And you see pictures here to the right. So the aim of this is to produce wrinkle-free and robust manufacturing. It's very efficient, and you do it the same way every time, so it's not labor dependent. This is a technique that they at Saab has been using since 1980 in the different fighter programs, but with time, more complex geometries has been in focus. And when we started looking into this, we had this particular case with the beam, where we saw that if you have a 40-45 plus minus 45 layup, as we have in the top figure there, and do a Hotep Forming, we get a really nice geometry. As you see this geometry, the beam we have, it's flat, but it has a recess zone here, meaning that all the material that is formed down from that side and towards this will be under tension here. We also saw that if you have a 0 layup or 0-90 layup, that you got really nice geometry afterwards. However, if you stack those two layers together, plus 45 minus 45, 0-90, the geometry comes, or the forming comes out with severe wrinkles. So these wrinkles do not depend on that you have too much material in this area, not primarily at least, since this distance is longer than that distance. So the wrinkles come from the different movement of the different layers. We have defined different kind of wrinkles. So we have the micro wrinkles that depends on how these interact, the micro level wrinkles. Based on this, we have started looking into the forming mechanism, trying to understand why this is happening. We have mainly looked at interply properties, the properties in between the layers, and how the material shears. Develop material model and put that into forming codes. So we have developed, or we have used the Uniform Composites forming method, simulation tools. We have developed detailed material models and been able to both predict wrinkles as you can see here, the very small wrinkles on the inner side. We can see them as stress levels in the simulations, but also see exactly which kind of fiber angles that comes out after forming. So based on that, we can actually understand and predict why this behavior happens. We saw that if we have a 45 minus 45 is 0.90, and you form the pairs in separate, you have no wrinkles. But if you start putting them together, you will have that. So we could also simulate and show that if you, instead of forming 2 layers at a time, we put everyone together, but we forced the layers that we knew gave us a good result to work hard together, trying to make the interface between the different stackings here weaker. We could do the same good geometry as we could when we did them 2 by 2. So the simulation could help us understand what happens, and we could kind of verify it. And this is quite important for future, that we can use the simulation before we go into doing a lot of experiments. And we can use them early in the manufacturing phase. Based on this, when we understood how everything was happening, we started looking into robotized forming, because a lot of geometries are still produced manually in their workshop today. And it's quite heavy work for those doing them. And it's a quite bad work environment. They can be really torn out in parts of their bodies. So we started looking into the initial structure that we had, the beam, which we knew gave wrinkles in certain layups. And we thought that since the Hotep Forming technology, it's kind of not that easy to steer. The rubber is going down and the materials is following. If we instead could really find a better forming method, a forming order with a robot, we could avoid these wrinkles. So that is what we did. We actually did the bad stacking without any twisting of the interfaces, and we predicted how the robot should move in order to avoid wrinkles. And we have managed that way to produce geometry which was 5 millimeter thick. I think it was 16 plies or something, without any wrinkles. So this could be a way of releasing the work for people also in the workshop in those applications when you cannot use Hotep Forming. We have also used the methodology for production of C-beam spars, as you see here, where we have made wrinkle-free forming of several layers and all different manufacturing fiber directions, although we have had a particular tool for kind of putting the material onto the flat part here. So where do we go now with our technology that we've developed, the forming simulations and the understanding of the mechanisms? Well, the next thing happening here right now is that we are collaborating with Volvo Cars, who are designing the Polestar Car. Polestar it's an own brand within the Geely family, as well as Volvo. But they are doing this design. And you can see that in the bottom plate, a lot of lower part of the structure, it's very similar, the Polestar 1, to the Volvo platform. It has, however, a few carbon fiber reinforced plastic parts, and the upper body is also made from carbon fiber composite materials, which is put together adhesively. So this is not a car I can afford. There's another Polestar 2, which is mostly metal, which is a little bit more affordable. So these are all electrical automotives. However, the requirements from Volvo is quite big. I mean, these are the kind of simulations and tests they are doing. They are testing, of course, a lot of cars, which is costly, but in their design, they must be able to predict what will happen. So the simulations are there first, and then they just verify that the simulations are correct. And in these simulations, they must have the correct fiber angles, and they need to know if they have some fiber waviness here and there after press forming. So right now we are looking into how to give them better material models for pre-break press forming, so they can put that into their modeling framework for crash simulations and component design. So when we did understand a little bit more of how this worked, how the forming, why we got wrinkles, etc. When we did hot rake forming, we felt that, well, why can't we push this a little bit harder? I said before, you should find a processing window for your application, your automation process. So started looking into if there was a possibility to, instead of having the hot rake former, use a quintus press, which is very similar, but instead of evacuating the air, you are actually using oil to press the membrane down towards the tool. So it goes very fast and you get a really high pressure. And the hope with this technology was just both to be able to produce components faster, but also, since we had such high pressure, we were kind of hoping that the voids would disappear, so we didn't need to go to autoclave for curing. However, what we saw was kind of not what expected. We saw that we had different kinds of wrinkles. You see here that the small wrinkles here are not of the kind we saw in the other geometries. They are at other places, and they are it looks like they are mainly due to that you're pressing away material. It goes so fast, so the material hasn't time to adjust. We also saw that the voids do not disappear because due to the very rapid process, we close the air channels before the air has time to go out. So we got worse quality and other kinds of wrinkles that was not within what we could predict. So in this case, unfortunately, no, we can't use this technology instead of autoclave curing for the components we are looking at for the moment. So that was the first part about find a processing window for the automation technology you have applied. When you had that, I said that you need to ensure that you have a good robust process and that the different parts fit well together. I'm basing that on that these predictive cost modeling tools that we developed, we also looked at the assembly process. And when you have an assembly like this with a lot of different spars that has to fit well together, it's easy that small shape distortion or radial thinning will make the fit not good enough, and you have to go to other activities to ensure that they fit within aerospace standard. And we saw that actually, if you have to do this, it adds up to 30% of the total part cost. So this is important, of course. Since we were mainly looking at the hot rake forming process, we started looking at what happened there. And we found that when you form different thicknesses of material, so hot rake forming 8 plies, 16 plies, or 32 plies, at different radiuses, using hot rake forming, we have the 2 millimeter radius and 6 millimeter radius. We could see that we had a certain change in thickness, which was quite large during the forming if you compare to the uncured thickness. During curing, you also had a small change in thickness, but it was not at all as large as you had during forming. and the total afterwards were often quite close to the thinning that we got during forming. So with that said, we do not need to put a lot of effort into the bagging during curing, because you always have to do that. That was a bad way of saying it. The focus here is to understand that the thinning has already happened during forming. So if it happens during forming, we also need to understand how we can avoid it. Looking at one of the pictures, this is a really bad picture from a high pressure forming experience. But if you start looking into different thickness of the layers here, you find that where you have the fibers going in this direction, of course the thickness has to remain more or less, because it's difficult to move these fibers, while the other layers where you have fibers going into the picture, so to speak, they had a tendency to move during the forming operation. So, and these movement or squeeze flow of layers, of course, is influenced by the temperature that you form at. So we started playing with temperature, trying to find the minimum temperature possible that could be formed without causing wrinkles in the flanges. Because if you have too low temperature here while you form, it will not be any sliding in between the layers, and it will wrinkle. And this study has cooked down to a study where we kind of have decided that for these kinds of beams that we are producing, you should actually only heat as much as you need at the area where you need. So heat the flanges only, and if we then keep the radius cold or at room temperature or even lower, we can actually maintain the thickness of the radius. And we can, of course, since we only heat a very small fraction of the component, we can make the heating process much more effective. So heating simply the flanges in different ways, single-sided heated or double-sided heated, we have done heat transfer modeling to kind of verify this. The studies we've done. We see that we get a much smaller radius thinning that we used to have, 4%, and we have reduced our heating time with up to 85% and still have a robust production. Now we are heating by doing conduction heating, heated plates. I can foresee that there are even more time to cut if you like, if you go for in some other heating technology here. It could be perhaps a local microwave heating, or even better, some induction heating using the new technology available. But with this technology, simple conduction heating, you can gain quite a big cost reduction and at improved quality, which is important. The second step, considering this having a good control over geometry, considers producing these spars. If you have a lot of spars that you want to join here, they can't have an outer surface that is rough. And if you cure them on a mill tool, a convex tool like this, it will have a bagging side here which is rough, and you will have pore fitting in between. It's preferable to cure it inside a female tool, having the big the outer surface shining and flat, and thereby be able to put them together. However, the uncured thickness, if you lay up a lot of materials like this in the ATL or AFP, there is a bulk factor that is remaining after forming, which when you put it into the female mold, need to be taken into consideration. First of all, these steps from flat layup to putting it up on a convex mold is simple. If you design this convex tool precisely the size that you have here, then you will get into troubles when you try to force it into the geometry. And as soon as the material softens up and you will debulk the material, you will lose the pressure. So what we did in this study was try to look at different approaches where we required some material sliding from up to down to cover the lower sides. So we looked at the possibility of having a gap, which is the kind of the way you have to do it. We looked at doing geometrical compensation of this forming tool, so that you had some excess length here that you, after when you cured it with a bag, you could press it down and force the material towards the corners. We also looked at the possibility of producing a forming geometry that looks like this, which made it easier to fit and with a different radius. And to see the material movement, we had used some gold particles inside the lamina, and we used a CT X-ray machine to track it and see the material movement. So doing this, we could actually see that if you have a small gap and a slightly curved web, as what we see here, the colors here become more unified, which means that it's a small difference in thickness afterwards, after curing, compared to the others. So this scale here shows the thickness scale. Another way of ensuring that you have a good fit is, of course, to know the shape distortions and the residual stresses, and we work in that areas as well, but that's not mainly related to manufacturing science that precisely. So I will not go that deep into it. What I like to say, however, is that we have looked into different kind of tooling technologies and tooling geometries. Often you think that if you have a composite material which moves differently in the plane compared to the outer plane cure, shrinkage, and thermal expansion is totally different from the in-plane. But normally what we used to say is that if you have a tool that behaves the same, this will not be an issue. The tool-part induction will be reduced. However, when we make a composite cure tool, we cannot make a tool that it's only like a U-beam as the component we want to produce. We need to stiffen it up with some backing structure. Either we have a stiffening structure like this, that is like we have in this picture. It can be free to move a little bit, or it's 100% stiff. Or we can have like a bend here on the surface, also providing a certain stiffness to the tool. And we have looked into these different options, different geometries, to see how they changes their shape due to thermal expansion or thermal loads during curing and heating up, and how that influences the component geometry. And we can find that compared to a simple L, which looks like that, depending on how hard you fit your backing structure with your curing structure, you will have quite high stiff stresses in your material. And today, composite toolings are considered very good, but maybe not as durable as you would expect. And we can actually see one of the reasons in this study. Considering shape distortions and geometrical tolerances, we actually have a very not automated, but very promising textile technique at KTH. It is a 3D weaving loom, which can produce 3D textiles in almost any geometry. It's totally integrated, all the fibers. You can go from 2D to 3D in one weaving setup. So it's very flexible. What we have used it for lately is to fill the T-joint sections called the noodle area or the fillets area, which is normally mainly filled with like a roll of prepreg or something. These fillets have a tendency, when you don't do it properly, that they crack by thermal contractions and differences in thermal expansion. And we have seen that if you instead use the 3D woven fillets, they become thermally stable, since you have fibers in all directions, so it doesn't move that much as you would if you had only fibers in two directions. It becomes more durable, and we can make an automated and robust manufacturing route. And this is a weaving technology from a small SME that hosts within our company, in our lab, and they call B-Team. So talking about composite manufacturing future lightweight applications, I've talked about the cost effectiveness. I said also that I want to talk about the challenge that we have with using several different materials, and I wanted this picture to visualize what I mean by that. This is a body on white, or the structure of a car, Volvo car, and you see all different colors there. They are different kinds of metals. They are all placed there. The different metals are placed there for a certain purpose, to give the right properties, the right weight, the right stiffness, softness, ductility, and weight, and of course cost. And I want to show this picture since we think that composites will be one of the future players in also the automotive industry. And we are, if we use the word competing, with a highly optimized product already. So what will it look like? We did an extension to our technical cost program, the cost modeling program, adding the framework of cost and weight optimization, adding a structural optimization model together with it. So looking into different options of making stiffened structures with different kinds of materials, doing an optimization route for that material to get the right properties, adding together the cost modeling software that I told you briefly about in the beginning, in order to have the optimized low weight structure. So giving us both the cost of the structure and the weight of the structure. So there are a lot of details here, a lot of subcodes and codings to make the different software work together, and I will not go into that. I just want to show you that we did a case study looking into two different applications that are quite far away from each other. Both something that could be an aerospace component, where we have a high requirement on low allowed deflection. We had another case which was a composite bottom plate for an automotive, where it's designed for torsional stiffness instead. So we allowed 3 different levels of deflection, or 3 different levels of torsional stiffness, and we had the different designs that you see here: the sandwich plate, the stiffened composite plate, and the pure composite plate, and try to find the cost and weight. And now come a really ugly picture that I will try to guide you through. So these are the results. what I want you to see is that on the y-axis here, you have the normalized cost, where the carbon fiber plate fulfilling the requirements, the different levels of deflection in this case, or the different levels of torsion in this case, is at the level 1, and all the others are at comparable costs. So they are smaller. If there's smaller costs, they are underneath, and if they are higher, it will be above. Meaning that, of course, we are aiming for something that is as low cost as possible. So hopefully in this area. On the x-axis, you see a normalized weight compared to the stiffness performance. In this case, it is in comparison, the weight is divided by the deflectional bending stiffness, and in this case, the torsional stiffness, since they're different cases. You see the carbon fiber plate, you see the stiffened design, and you see the sandwich design. When it comes to the very high demands of a flying big airplane, the carbon fiber plate is good. The stiffened design is even better, but actually in some sort of occasions where we do not have the very highest demands on low deflection, also the sandwich design can do the right performance, but also at very low cost. So based on what we saw in this case, we could see that the stiffened design is always possible to make and will give us a good outcome. Of course, that's how they have always done it, with some option to change the sandwich design in some cases if the demands aren't too big, so to speak. The same could be said with the torsional stiffness, that the sandwich design is very competitive also for that. The stiffened design becomes doesn't really work in this case. We need to improve the modeling on the torsional, and the carbon fiber plate is providing a good result, but it will also be quite costly. So adding some other optional materials here, like there, you could see that there are options with lignin-based carbon fiber if they are done in the correct way and given good properties. They could provide a good cost option in the future. The hemp fibers, they are low cost, but they are not providing the same weight to stiffness performance. So they are not interested in this case. And actually, to be honest, in this bending stiffness dominated case, there is nothing that really beats the sandwich in the stiffness design. When we come to the torsional stiffness in the car, on the other hand, we see that the hemp fibers are very competitive. And if we bring in recycled carbon fiber, maybe from actually worn out fiber here, we can see that is also a very, very interesting material system. So this was a very, interesting case to do, totally fictive, but we learned quite a lot, and we are now bringing it with us for the next step where we want to do design for sustainability. So today in the existing framework, we are minimizing the cost. But what we're planning to do now and starting is to instead minimize the energy consumption or perhaps the carbon dioxide footprint. So instead of cost coming out here, we have that measure to be put into the minimization, and we will have a cost, weight and carbon dioxide footprint coming out as a measure. It is interesting to notice that cost and sustainability often goes hand in hand, since if you can reduce the heating of a certain material, you of course reduce production time and you reduce the energy consumption, which also reduces both cost and carbon dioxide. So often looking for sustainability could give you also some more money back. We have looked into recycled aerospace carbon epoxy and other grades to see if there is an economical and mechanical potential for recycling, just because we wanted to put a number on how much it would be worth and what kind of mechanical properties we could have from it, looking into literature and what recent research has said, and we have put that into the framework already. When we talk about design for sustainability, we talk about multi-material and biomaterial solutions, and they are perhaps cost effective, but we need to also consider how to recycle them. One option would be to use a single material system as this one, where we have self-reinforced PET composite stiffened by PET, overmolded PET, which has been done in a 2-operation step, where we do the composite plate first and the stiffeners by injection molding. This has been studied for a wind deflector for a truck, having promising both weight reduction and cost using the particular material system. So the self-reinforced PET in this case would be both fibers, matrix, and the stiffeners, which means that we have a single polymer material that could be recycled afterwards.
Malin, we have quite a few questions for you as well, so I hope you...
Yeah, I need to stop. I just want to say something about the very last thing,
Good.
Which is about the multifunctional materials. So I think in the future we need to consider using materials not only as a structure, but also for other things. And multifunctional materials means that you are utilizing it in a good way. What we are working on here is the lithium-ion battery, where a little bit of electricity can make the lithium go from the positive electrode to the negative electrode. And we are researching the possibilities of using carbon fibers and the polymer matrix to do so. We see that there are a great potential for certain fiber systems, and particularly this one maybe, to be charged by lithium ions. And we have already the system going where the matrix has been made stiff, so it's a load carrying system. And we are looking into the potential mass savings ranging from 5 to 65% for different applications. And on top of that, we are going to do work a little bit more on the multifunctional materials. We see that they work as piezoelectrical sensors. They can be used as actuators, used for energy harvesting, etc. And that's quite futuristic, but it is something we have to consider and take into consideration in future manufacturing, of course. I will skip that picture. So, to end, so we have time for questions. Composite manufacturing in future lightweight design needs to be cost effective, right level of automation, expand that to its maximum point and make it robust. It will be used, you will use several different materials. I'm a little bit worried that we sometimes sub-optimize and think that biomaterials are the best. But when it comes to recycling a thermoset material with bio-based material, I find that could be also quite tricky. So maybe we make it difficult for ourselves if we do not look at the big picture. And we will have to deal with the multifunctional materials and structures in the future, because these structural batteries, for example, when they start existing as panels in our cars, that is something we need to deal with in the manufacturing. I have put a link for inspiration that I will not show, here, but that will follow the presentation. If you see it, you can have a look, see more about the structure of batteries. I want to thank you all for listening, and thank to my colleagues at KTH.
Thank you very much, Malin, for a very exciting, interesting presentation. We'll rush on to take some questions. So we have a number there, and some of them are quite short, so you can also answer them in a short way. The first one from Mike Elkington, and he said on page or slide 13 shows a robot forming apply onto a mold. Is that a single curvature?
Sorry, it is a single curvature.
Is the mold? So slide 13 is double or single curvature?
We have done both.
You've done both.
Yeah, we've done C-spars where it's double curved.
Okay. Next question is from MD Vasquez. What type of resins have you worked with?
We are mainly working with thermosets. We have done some thermoplastics where we work with the SR PETs, for example. We have worked with some thermoplastics considering where we try to compare different properties with the 3D woven geometries. We have also used nylon, but we are mainly working with epoxy and similar structures. Yeah, mainly epoxies or similar aerospace graded materials. We work with the materials that our colleagues work with in the industry.
Yes, of course. And next question is from Danobat. Did you work with dry textiles, non-crimp fabrics, wovens, etc.?
We do a lot of work in our workshop with these materials, particularly when we build things together with our students. We have done some work in research, but not a lot.
Okay.
We work with the 3D woven geometry, of course, is totally dry. So there we do infusion afterwards when it has been woven.
Okay, thank you. Isa Imami's got a question. She says, thank you for your presentation and interesting studies. And the question now comes, does heating flanges with the induction method and keeping the radius cold cause any distortion in your final product?
You're talking about shape distortions.
Yes, I think that's the question.
Yeah, we studied that, and we couldn't see any influence on the shape distortions from the local heating, the tailored heating.
Okay.
So no, not as far as we've seen.
Okay, that was clear. Louis Barmont asked a question. He starts by thanking you for your interesting talk. Could you elaborate a bit into the infrastructure and cost of the simulation codes you understand these processes? Are they homegrown codes, off-the-shelf codes, or are they integrated with commercial FE? So maybe a few words about the modeling framework you showed. Is it all?
Yeah. So it's Python code in the base. We have a CAD on top of that we use for checking the complexity of different geometries that we get. We are combining it with FE code for optimization and structural design. So it's a mixture, to be honest.
It's a bit of a mixture, yeah?
Yeah.
Okay. I hope that answers your question.
Yeah.
The next question is from Fabricio Brisson, and he starts by saying, awesome presentation, Professor Malin.
Thank you.
You mentioned that Aniform software was used to forming simulation. I heard that the Aniform was not able to simulate thick layup off the shelf yet. Did you improve the modeling algorithm to simulate 6mm thickness?
To be honest, we bought a new computer with a much more RAM. We had problems with the thicker layups since we wanted to study every single fiber direction separately. Otherwise, they have methods for homogenizing that they recommend, and I think there are good possibilities from using them as well. But if you want to do like we did for research purposes, you have to simulate every single fiber layup, and it becomes very heavy calculations, but we use them the way they were.
Okay.
but it took a lot of memory.
It took a lot of memory. So
yeah.
You solved the problem by upgrading your hardware.
We paid for it. Yeah.
You paid for it. Yeah. Marquez has a question. He starts by saying, "Very interesting presentation." And the question comes along now. It's a bit long one. Optimization process depends obviously on the cost function and objectives. So that would be cost, performance, topology, etc.
Yeah.
How do you deal with your objectives within the optimization process?
Oh, this is done by my colleague Matilda Karlsson Hagnell. She started this as a PhD student project and has run it as a postdoc now. Exactly how she's doing it, I recommend that you look into her papers to see that. I'm afraid I can't answer.
And the papers have been quoted on at the bottom of your slide.
Yeah, most of them. Yeah.
So there's some more detailed questions from Marquez on that single process, a multi-objective one. Refer to your colleague. Yeah. Okay. We have a question from Hussein Abbas. What's the advantage of epoxy that encouraged you to use it over thermoplastics? I don't know if that's what if you have an answer to that.
Well, I can tell you that we have in Sweden a car called the Lucia car. Was made by Volvo around year 2000, and it's standing I've heard in the basement of Volvo. Sorry, it's made of thermoplastics, and it's looking really sad because it has creeped. So it has creeped and kind of sagged. It is difficult to make the aerospace structural components, as far as I've understood. The high demanding components without any creep. You have to go for really high temperatures, and I think when we start learning how to use thermoplastics, maybe we should do that in the automotive, based on the needs in the automotive industry. Okay.
There's a couple of questions more. We are running over time, but I'll allow to take them. So the next one is for Richard Butler. Thank you, Malin. Very interesting.
Hi, Richard.
We have seen a length effect in forming your spar with 0-degree fibers in a 6 meter long part.
Oh.
This was overcome using a matched stiffness laminate with non-standard fiber angles. Do you have any views on the industrial uptake of non-standard angle laminates? So funny angles.
Yeah, funny angles. It becomes more difficult when you have small angles and you can't use the intra-ply shear possibility, of course. This is something you can play around with and see if you can get around by putting the stack up in an intelligent way, and it sounds like that's what they have done there. So congratulations, sounds good. I haven't heard that we are allowed to go from non-standard fiber angles in the cases where we have worked with industry, but on the other hand, when starting working with automotive industry, they don't have the standards. So there is also an option to start playing around with these things, but I don't think it will be something as long as 6 meters.
Okay. And the final question, which hopefully can be answered, this is from Siaur Khan, and he says, thanks for a very nice presentation, Professor Malin. So he says then, as of now, carbon fiber is used to reduce cost and sustainability, and I guess reach sustainability or something like that.
Yeah.
Be the next step. Any idea? So
you're thinking about reducing cost by recycling. Is that what he's after?
I guess that's probably what it's about.
Yeah. I think we can have some few ideas, but what I think we need to do is use the long fibers where they need it, and the recycled and short fibers where you do not need the same properties, but maybe you need to do a stiffening structure as we did with a SRPET, for example. So I think the future will be to combine these, and if we keep the same material, it would be easier to recycle as well.
So he also mentions carbon fiber, and it could be also part of the question is about did you see any mileage in recycling other types of fibers, glass fibers and so on, which I'm not sure in your applications. Yeah, we haven't seen any good results with recycling carbon fiber. I've seen that it can be a hazard having glass fibers. Sorry, I haven't seen any
good results from recycling glass fiber. We have seen that it causes problems in the recycling if you have glass fibers there. It melts and become a mess in the bottom of the heating oven or something like that. So and how natural fibers, bio-based fibers work, we haven't tried, but I can foresee that it's a bit difficult. So we need to find a good matrix that can survive with the fibers, and we can use it all over again. We have a challenge there in the material development side, I would say.
I would, yeah, that sounds very, very sensible. I think there's some significant challenges there to overcome yet. So more research needs to be done. So I think this will have to stop now, and we run out of questions. So that's great.
Great.
Thanks so much for your presentation.
Thank you.
It was very interesting and gave a very broad perspective on the work and your thoughts about where we're going with this.